A BCD counter is just a modulus 10 counter that can go from 0 all the way to 10. And sometimes it is referred to as decade counter because it counts to 10. So let's see how we can build one in Verilog. So I started a module, I called it BCD Counter. And it takes an input clock, a reset, enable, and done. We'll talk about this in a second. And the count itself. Okay, so what really is a BCD counter is just a modulo 10, and since it doesn't change, I don't need to have it as an input or parameterized. I'm just going to hard code it. So I'm going to base my code on the modulus counter that is hard coded, or like the one that we basically put an 8 or a 7 in here. So I'm just going to copy this code in here. I'm just going to take it, we'll just paste it in here, and that's how we're going to start it. So just as a reminder of how it's actually done, it's actually a register. This is the register part, and then I'm going to do the done. But now the done is very specific. I wanted to actually go from, it's a modulus 10, so it has to be, the final value has to be 9. So I'm going to just hard code it as a 9. But now I will just expose this done. So in the previously we have done this as wire, but what I need to do is I need to expose that done because it'll enable me to cascade the BCD counter in this particular configuration, and in this way I can get a multi-decade counter. And all I have to do is just remove this part from here, and now I expose the done signal to the outside world. So done is usually asserted whenever the final value or the value of the registered or the counter is actually at 9, and that's how we can get it. So now there's an issue here that it doesn't like. Let me just fix that. I think it's because it needs bits -1, so we need to fix that. I don't need many bits. All I need is actually 3 bits, so I can hard code this one here. Okay, and that's how a BCD counter is. So this configuration here that you see is what we call ripple counter configuration. Like I'm basically connecting them in a cascade order. This particular configuration will give me a multi-decade counter. It might not be the most efficient way, but it's really highly structured, and it's made in such a way that I can just create a generic multi-decade counter. What do I mean by multi-decade counter? It's a counter that can go all the way from 0, 0, 0, and each one of the counter can go to 999. So it actually goes from 0, 0, 0 to 999 in decimal, basically. It's kind of like a decimal counter that can go all the way through. And it's made in such a way that I can actually take that signal in here, which is the final done signal from the final BCD here, and I can just connect it to a different version or another instance of this and connect it to the enable in here, and I'll create a 6-decade counter that can go all the way from 0, 0, 0. It'll go from 0, 0, 0, 1, 2, 3, another one, all the way. It can go to 999, 999. Okay, so I can just cascade them. That's why I created it this way. So I went ahead and actually wrote the code for this cascade version on multi-decade counter. And what I did is I just, as you can see, I instantiated 3 instances of the BCD counter themselves, and I created these signals in here, which is just an AND of like every couple of signals. So I'm ANDing this, and I'm ANDing this, and I'm ANDing this. And of course, the very first one in here, we can just create it as an enable. So I exposed this and I made it as an enable in here. So that will allow me to count or stop the counting within counter, or actually just cascade it and connect it to a previous stage as well with like another 3 of them. And here I have the 1s, the 10s, and the 100s. Each one of them is 4 bits basically, which will give me a number between 0 and 9. And that's how we can create a multi-decade counter. Again, each one of these BCD counter is a decade counter that can count from 0 to 9 only. So I created a test bench to test this functionality. Let's see how it's actually performing. So here's the result of that, and just so that you know what I've done, I just created a clock signal in here, and it's just one multi-decade counter. Basically, it's the one that you see in here, which should count from 0, 0, 0, 999 to 999. And I just basically reset it for a while and then stopped it, and then I just repeated it to 115, approximately 115 counts. That's what I expect to see. So what do I see in here? Well, I can see that the enable signal is in here, and then the reset signal, and then done is actually never done. I don't believe it's ever done, and the reason why is because we never reached the 999. Okay, that's the only time when it will be actually done. That's the only time when this done signal will be. So now we take, this is the done that is actually exposed to the outside world. So the outside world doesn't see the internal done, so all it sees is the following signals in here. So I'm talking about this particular done, and this particular done is only done when my BCD counter is at the very final value, which is 999. So what does it see in terms of the 1s and the 10s and the 100s? Well, the 1, as you can expect, it should actually go Let me just zoom a little bit. It goes 0, 1, 2, 3, 0, 1, 2, 3, while the tens is at 0. So that's that. And then the hundreds is at 0. Okay, and now what about here? Well, what's happening in there, it's going, this is the tens, so this here is whatever you see in between these two here will be the 10, 11, this is basically the 1, 0, that's 10, 1, 1, that's 11, 12, 13, 14, 15. Okay, you get the idea. These are the tens, so these are the 30, the one from here to here, from this particular moment, which is 122 nanosecond, all the way to here to 162 nanosecond. It's actually the 30s, the 40s, the 50s. And I'm asking it here in the simulation, I'm just asking it to go to 115, just so that I see the last one actually operational. And you can see that it's actually going to 1, and then 105, 101, all of them will be here. And then I want 115, so the tens has to be 1, and that's what you see in here. And then I want it to go to the 115. It's actually going a little bit longer because I'm actually waiting for 20 nanoseconds more. So actually the final value it sees is 1, 1, and then, or actually it's a 1, 2, 0. So it's 120. That's the final value it sees.